Hi. Today we are going to talk about proving trig identities. I have posted on our Canvas page this sheet of chapter 5 identities. I've written down the reciprocal identities and the quotient identities here on my board. I'm going to erase them in a second. You're going to want this handy when you are working on this assignment. So you'll either need it up on your screen or print yourself a copy. We're going to use the ones on the front side of the sheet for today, only down to here. And then we'll talk about the sum difference and some of the stuff on the back, or the second sheet. We'll talk about those next week. So today we're going to talk about what's considered the basic trig identities. So these are the reciprocal identities, which we already knew, or we have already played with them a little bit as we worked through chapter 4 and all of that basic trig stuff. The tangent equaling the sine divided by the cosine, the cotangent equaling the cosine divided by the sine. We've briefly talked about that, but not a ton. And then the other three sets, one is called the Pythagorean identities, one is called the odd-even identities, and one is called the cofunction identities. Those are new to us today. So again, you can find those posted on our Canvas page, a copy of all of the identities. They're also in the book, section 5.1. Okay, so basically what's going to happen is you're going to be given, you have a worksheet, so you're going to be given something that looks like this. This is what's called an identity, and our job is to prove that the two things are in fact equal to each other. So generally, we start on one side of the it's not an equation. Don't consider it. It's not like you can, or you don't want to do things like add to both sides, multiply by both sides, things like that. You don't want to do that to solve an identity. Your job is to figure out how to make this side look like that side. Or you can make them both, change both of them so that they're the same. We'll talk about something like that as well. So first of all, you might notice that the cotangent is the same as 1 over the tangent. And what's happening between the cotangent and the tangent is multiplication. I know that because the two things are smashed together. We don't necessarily use a multiplication symbol, right? But this is the same as the tangent over the tangent, which is equal to 1. So straight across, tangent times 1 is tangent. This is a tangent over 1, so 1 tangent times 1 is tangent. Tangent over tangent is equal to 1. Once you get to this point where you've said, okay, look, I showed it's equal to 1, you can do one of three things. You can just put a little check mark to say, look, I did it. You can use a little box like this, a little shaded in box. That's also a good way of showing that you finished your proof. Or fancy would be QED. It's QED is what's the language? Not English. I'll come up with it in a second. To say I've proven it or I've shown it. Okay, so here's another example. Okay, so what you want to look for as you're working through these is some kind of a clue as to which kind of identity you might use. So this little squaring right here, the Pythagorean identities, if you look at them, they look like this. Cosine squared plus sine squared equals 1. 1 plus tangent squared equals secant squared. Cotangent squared plus 1 equals cosecant squared. So the little squaring, the little 2 right here, is my clue that I want to use my Pythagorean identity. My Pythagorean identity looks like this. So what I can do is I can take out this 1 right here and replace it with a cosine squared plus a sine squared. Oh, we have x's. I don't want thetas. I want x's. Sorry. And so then up here, I still have a minus cosine squared. And on the bottom, I still have a sine squared, or a sine, just a regular sine. Sorry, kicking my dog out. Okay, so then what happens with the cosine squared minus the cosine squared? And so I have sine squared over sine. And the way that works, let me erase this. Sine squared is the same as, when we have the little 2 right here, that's the same as the sine of x squared, or the sine of x times the sine of x. Okay? So what I have right here is the sine of x times the sine of x over one of them, leaving me with just a sine. They cancel. So that's what I was looking for. I'm finished right there. I'm going to erase this. I'm going to put this up again in a second, after we do another problem. So. So this one says the secant of negative x, the cosine of negative x is equal to 1. So like earlier I said, you want to look for a clue as to which set of identities you're going to use. This little negative right here is a clue that you want to use your odd-even identities. So notice that the secant, where's it at right here? The secant of negative x is equal just to the secant, and the cosine of negative x is equal to just the cosine. Odd-even identity, I can replace the secant of negative x with just a secant x, and I can replace the cosine of negative x with just a cosine x. And then secant is the same as 1 over the cosine. That's my reciprocal identity that I had on the board at the very beginning, times the cosine. They cancel, and I'm equal to 1. And that is what I was looking for. Yep. So you want to think of this as the same thing you would do if you had like 5 plus 2 in an equation. You can combine the 5 plus 2 and replace it with 7. The 5 plus 2 and the 7 are equivalent, so I can take the one out and put the other in its place. It's exactly what we're doing here. We're just taking something out and replacing it with something that it is equivalent to. So let me give you another example. Okay, so same idea. The clue that I'm looking at is the little squaring on the secant, tangent, cosine, sine. So again, that would be the Pythagorean identities. I can replace the secant squared with a 1 plus tangent squared. That's the Pythagorean identity involving tangent and secant. So I still have the minus tan squared right there. And then the cosine squared plus the sine squared, that's in fact equal to 1, again, using our Pythagorean identities. So what happens to the tangent squareds? They cancel out, and I'm left with 1 over 1, which is 1, and that is what I was going for. sine x minus the tangent of x times the cosine of x. Oh, I'm going to have to erase that one. I don't have enough thing. Cosine plus the cosine of pi over 2 minus x. All of that is equal to the sine of x. Okay, so this cosine pi over 2 minus x is one of our identities. That's called the cofunction identity set right here. You can see that the cosine of pi over 2 minus theta or minus x is equal to the sine. So we can take this whole thing and replace it with a sine. Now, this doesn't have any other hints for me to tell me which identities to use. And if there are no hints as to which set of identities to look at, then you just look at the reciprocal or the quotient identities. So since I need to get to sine, and I have a sine and a cosine here, what about the tangent? How can I change the tangent to something involving sines and cosines? It's the reciprocal or quotient identity that says the sine of x divided by the cosine of x is equal to the tangent of x. And that is being multiplied by the cosine of x right there. So the cosines cancel, and I have sine minus sine plus sine, which simplifies to just a single. Two of them cancel, and that's where I'm finished. Okay, so I said I was going to talk a little bit more about that idea of a squared function. So just note, as we move forward in some examples, that the sine squared is equal to the sine squared, which is the sine times the sine. So I mentioned that a minute ago. Well, what if I have something like the tangent squared? Now here we changed the tangent into the sine over the cosine. So what can I do with tangent squared? Well, tangent squared is the same as the tangent squared, like that, right? But we know that the tangent is the same as the sine over the cosine. So how do I, if the tangent was squared here, the sine over the cosine is squared, and then I can write it as the sine squared over the cosine squared. That's true of anything. So if I had, for example, the cosecant squared, and I know the cosecant is the reciprocal of sine, this is the same as 1 over the sine squared. So as long as you keep the squaring, you can use the same reciprocal identities and quotient identities as you would use if there wasn't a little squaring there. So tan squared is equal to sine squared over cosine squared, and then any of the reciprocal identities work the same way. I'll leave that up for just a second. Okay. Okay, so this is the sine cubed multiplied by 1 plus the cotangent squared of x, and that's supposed to equal the sine. So looking at my Pythagorean identities, I can replace that with a cosecant squared. And then we know that cosecant squared, using this identity right here, is the same at, or rule, I guess it's more of a rule, it's not an identity. I can use the reciprocal identity to change the cosecant to 1 over the secant, and since the cosecant is squared, the sine is squared. And then I have that multiplied by the sine cubed. So when I multiply them together, I get the sine to the 3rd power over the sine squared, and these two cancel two of those, and so I'm left with just the sine. The same way, if you had like m to the 5th power over m squared, the two of these cancel two of theirs, and I'm left with 3, right? If this was m to the 3rd power over m squared, I'm left with 1. Same idea. 3 on the top, 2 on the bottom cancel, leaving with 1. The hardest thing about doing all of this, proving trig identities, is using your regular algebra skills combined with this kind of confusing sine, cosine function, trig function. So remembering that your algebra skills work here as well. So 1 minus cosine, and then 1 plus cosine, all over cosine squared is equal to tan squared. So what we're going to do on the top of this function is we're going to multiply out this FOIL using our FOIL method to multiply together two binomials. So 1 times 1 is 1, and then I get plus cosine. A negative cosine times a 1 is a minus cosine, and then a negative cosine and a cosine makes a minus cosine squared. Now, lots of temptation to cancel out these cosine squareds. You cannot cancel out those cosine squareds. You can, however, cancel the cosine there in the middle because they simplify. I don't want red. So now I have 1 minus cosine squared over cosine squared. And then remember our Pythagorean identity that says cosine squared plus sine squared equals 1? We can rearrange that. And if I move the cosine squared over there, then I have sine squared equals 1 minus cosine squared. Anytime you see a 1 minus cosine squared, you can replace it with a sine squared using this Pythagorean identity. If you have your paper printed out, you might even write over here on the side, write this one, and then moving the sign to the other side, you could simplify it or you could rewrite it as that. These three are equivalent. They're just different representations of the same. So 1 minus cosine squared is the same as sine squared. So this becomes sine squared over cosine squared. And as we talked about a minute ago, that is in fact the same as tan squared. So that's where that finishes. So rearranging this to look like these two, the other two Pythagorean identities, you could rearrange them in a similar fashion and rewrite yourself a couple more versions of those, and they might be helpful as you work through your questions. Okay, so the last two examples I have are really to talk about more about some algebra stuff than to necessarily simplify. So this first example I have for you, we're trying to get the secant and the tangent to the cosecant. Well, secant and tangent are related in the Pythagorean identities, but those have a little square, so we wouldn't use that. Since there's no little squaring to tell us to use the Pythagorean, there's no little negative x to look at the odd even, there's no pi over 2 minus x to look at the cofunction, then we should just stick to the top two. So the reciprocal and the quotient are the most commonly used. I'm going to erase this because I think it's going to be on my way. And so looking at our reciprocal, we can change the secant into 1 over the cosine. And we can change the tangent. I could change the tangent into 1 over the cotangent, but that's not going to be helpful here. So I'm going to change it instead to the sine over the cosine. So why did I choose this instead of 1 over the cotangent? Well, my answer is in cosecant, and I know that I can get to cosecant if I have a sine in my equation or in my expression. And here I have all sines and cosines. So that's kind of if you don't know what else to do, change everything to sines and cosines. Most helpful. So cotangent, not going to be helpful in this case. I need sines and cosines. Okay, so what do I do when I have a fraction divided by a fraction? Well, that's the same as 1 over cosine divided by sine over cosine, right? So what's our rule of division of fractions? We can rewrite that as multiplication of fractions by flipping over the second fraction. So sine over cosine, flip the guy and multiply becomes cosine over sine. Then our cosines cancel. We're left with 1 over sine, which is the cosecant. Last example I have for you, we're going to, again, look at some algebra, basically, combined with. So what do we do when? So here was a situation where we had a fraction divided by a fraction. So we flip the guy and multiply. In this next example, we're going to come up with a common denominator. So again, an algebra skill that could trip you up if you haven't seen it, used with these identities. Okay, so tan plus cotan equals cosecant times secant. So again, like I did over here, I'm just going to work on the left-hand side. I'm going to try to make it equal the right-hand side. I'm going to switch this stuff to sines and cosines. So the tangent is the sine over the cosine, and the cotangent is the cosine over the sine. Now, in order to add these two fractions together, I need a common denominator, right? So this fraction has a sine, so I'm going to multiply it by sine over sine. And this fraction has a cosine, so I'm going to multiply this one by cosine over cosine. And remember with fractions, when you multiply two fractions together, straight across and straight across. So when I multiply these two together, I get sine squared over sine cosine. Then here I get cosine squared over sine cosine. Now that I have a common denominator, I'm going to put them together in one fraction. Now, do not be tempted, or don't give in to the temptation to cancel some sines and cosines right here. We cannot. Why is it okay to cancel over here where there's a cosine on the top and a cosine on the bottom? Because it's straight multiplication. I have a fraction multiplied by a fraction. That means on the top I get cosine, on the bottom I get cosine times sine. It's all multiplication. Why can I not cancel them here? Because of this addition in the middle. It doesn't allow us to cancel things the way we would like to. So what do we do instead? The little squaring, tells me I should look at my Pythagorean identity. Now, if you look at the Pythagorean identity for cosine and sine, it says cosine squared plus sine squared equals 1. It's okay to replace this with a 1 even though it's backwards, right? Because Sine squared plus cosine squared and cosine squared plus sine squared are the same thing. So I have 1 over sine cosine. Now, am I there? Have I finished? Well, take a look at where we're trying to go. The cosecant is 1 over the sine, and the secant is 1 over the cosine. So what I have here, is it the same as what I'm trying to get to? Yes, in fact, this 1 over the sine is the cosecant, and this, use a different color, and this 1 over cosine is the secant. Why is it okay to put 2 1s on the top? Because there was a 1 there, right? And 1 times 1, right? Still 1. So I didn't change anything. That's the answer there. Okay. That's what I have for you today. Let me know if you have any questions.